Okay, welcome back everyone. In this video, we're going to continue our discussion of periodic motion by talking about the simple pendulum. So what we're trying to figure out this time is how to analyze the motion of a simple pendulum and how it is simple harmonic motion. And we're also going to look at the characteristics of a physical pendulum. So here's a simple pendulum. You have a point mass suspended by a string. Now the string, we pretend like it has no mass and you can't stretch it. So if the pendulum swings with a small amplitude theta from the vertical, it is simple harmonic motion. And we're going to prove this very quickly. Okay? First of all, if we look at our forces here, tension and mg cosine theta are not going to be equal to each other. They're going to cause centripetal acceleration, but they are not restoring forces. The only restoring force here is going to be mg sine theta. Okay? So if we write F net equals ma in this case, we would say negative mg sine theta, because it's to the left, is equal to ma, which is going to be m d squared x dt squared. Okay, so what I'm saying is that at this point the displacement would be in this direction, but the force would be in that direction. Okay, so even though the force depends on the sine of the angle, we're going to say that the actual acceleration will be in an x direction, where x is tangent to the path. So that's a little weird, but just go with it for a moment. And one thing we're going to say is that the sine of theta, when theta is less than or equal to about 15 degrees, we can approximate that the sine of theta is approximately equal to the angle itself. And you're actually going to be very close. It's called the small angle approximation. And you're going to be off by less than a few percent until you get up to about 10 or 15 degrees. So that means that sine theta turns into theta. So negative mg theta equals m d squared x dt squared. And as a matter of fact, the Taylor series expansion for sine theta is theta times 1 plus 1/4 sine squared theta over 2 plus, well, a bunch of other stuff that we don't need that will have basically sine to the 4th of theta over 2. And so the point here is that if theta is small, all these other terms will basically drop out and we'll just get theta times 1. So that is the small angle approximation. And if this is true, well, what's another way of writing theta here? Theta is approximately equal to x over L. So negative mg x over L is equal to m d squared x dt squared. Okay, now at this point I can cancel the m's. I could have done that a long time ago. And I can also write negative g over L times x is equal to d squared x dt squared. Maybe it's better if I write it in the other order, because that's what we're used to seeing. D squared x dt squared is equal to negative g over L times x. Okay, now where do we recognize this from? Well, this is simple harmonic motion with this value being equal to omega squared. So omega is the square root of g over L. And so we really do have simple harmonic motion with this pendulum. So let's see how we would use this. Let's find the period and frequency of a simple pendulum 1 meter long at a location where gravity is 9.8 meters per second squared. So we know that omega is the square root of g over L. Okay? And that means that t is 2 pi over that, so 2 pi square root of L over G, so 2 pi and then root 1 over 9.8, and that's going to get us just about 2.01 seconds. Well, we have 4 sig figs, so we'll write it. It's actually 2.007 seconds. The frequency is therefore 1 over that, which is 0.4982 or 3 hertz. So somewhere in that range. Okay. Then we can also talk about a physical pendulum. Now, a physical pendulum is not just a point mass anymore, but it's a real pendulum that uses an extended body instead of a point mass. Okay? So it's got a pivot, and it's an irregularly shaped body. And instead of having a restoring force, we are going to have a restoring torque. Okay? And the way that this works is that the torque is going to be basically RF sine theta, where R in this case is from the pivot to the point of application of the force, which in this case is mg. Okay? Now, the portion of that which actually contributes to torque will be the perpendicular component, mg sine theta, because mg cosine theta is parallel to R, so it has 0 torque. Okay, so we continue with this, and R is basically D, and F is mg, so we have mgd sine theta, and we also have a negative sign from the right-hand rule. Put your fingers along R, curl them towards mg sine theta, and the torque is actually going to go into the page. Okay? So, because of that, we can write, again, that sine theta is approximately equal to theta. And we also know that torque is equal to I alpha. So we can write negative mgd times theta is equal to I alpha. But alpha is to acceleration as d squared theta is to d squared x. If that didn't make any sense, what I'm just trying to say is that alpha is actually going to be d squared theta dt squared. Okay? And so if we rewrite this in the way that we're familiar, so d squared theta dt squared, that's going to be equal to negative mgd over I times theta. And lo and behold, here is omega squared for the simple harmonic motion. So that means that omega is root mgd over the moment of inertia. Cool. So now we have another way to analyze pendulums. Okay, so we just went through this, how the physical pendulum is a type of simple harmonic motion. So that was on the previous slide. But let's do an example. What's the period of oscillation of a meter stick if it has a pivot at one end? So if it's acting like a physical pendulum. Okay, well, first of all, we have to note that the center of mass of this is in the middle, and so that is where the force of gravity is going to act. Okay, so this R right here will actually be half a meter. Okay, and we know that omega is the square root of mgd over I. This means that the period is 2 pi over omega, so it'll be 2 pi times the square root of I over mgd. Okay, now I, when we're pivoted around the endpoint, I for a rod is 1/3 ml squared, and d in this case is L over 2, so we can put that all together to say that t is 2 pi times the square root of 1/3 ml squared over mgl over 2. Okay, so we'll cancel this out. The m's will cancel, one of those l's will cancel, and we're going to get 2 pi root 2l over 3g. So that is the period of a meter stick. Notice that the mass cancels out. It has no effect on it. Okay? So one cool example of a physical pendulum, roar, the leg of Tyrannosaurus Rex. Okay? So the leg length is L, and it acts as though it's pivoted right here. And so you can actually figure out a lot about dinosaurs and their motion by analyzing them using the ideas of simple harmonic motion. Okay, now next time we're going to wrap things up with a discussion of damped oscillation and forced oscillation.